Hi class. In this lecture here we want to continue talking about applications of differentiation by talking about increasing and decreasing functions, and then we're going to talk about what's called the first derivative test. Okay, so what we're going to do in this section. So the first thing we're going to do is we're going to determine intervals on which a function is increasing and decreasing. So this activity here I'm going to break into two videos. The first lecture, so video 1, will be intro and simple examples. And then I'm going to follow this up with another video, which is just going to be more complex examples. And then the final video for this section is I'm going to talk about something called applying the first derivative test to find relative extrema functions. So we're going to learn about something called the first derivative test. Okay, and this will be video 3 with examples. So we'll go through this across these 3 videos. So he'll be the first one. Again, we're going to intro and we'll do 2 very, very simple examples so you can see the concepts. Okay, so what is the definition of increasing and decreasing functions? So a function f is increasing on an interval. Okay, for when any 2 numbers x1 and x2 in the interval imply, what happens is when x1 is less than x2 implies that f of x1 is less than f of x2. So what this kind of looks like, what I'm hitting at here, is if you have a graph and here's x1, here's f of x1, here's x2, here's f of x2. Okay, I'm sorry, f of x2 is over here. Really what this is saying is, look, whenever you have x1 is less than x2, well then f of x1 has to be less than f of x2. The way I like to think about this, though, when I look at graphs, is as you move to the left, so as you move to the right, as you increase x, as you go from x1 to x2, so you're moving to the right, the function goes up. So as x increases, so does f of x. That's the way I like to think about it. So decreasing is just the flip of this. A function f is decreasing on an interval when for any 2 numbers, x1 and x2 in the interval, x1 being less than x2 implies that f of x1 is greater than f of x2. So kind of, I'll do a very similar graph here. Here's x1. Up here will be f of x1. Here's x2, which is greater than x1. But down here will be f of x2. So look, what this means is as x increases, okay, so as you're moving left to right, okay, f of x falls. Okay, so the way I like to think about it is, if you were going to imagine a person, I know this is silly to think about, but imagine a person was walking along the graph. As they go left to right, they're going down, so they're decreasing. Here, if you have that person walking on the graph, I know it seems silly, but as you go left to right, okay, the person's walking up, so the function is increasing. All right, so this is how this all relates to the slope of the function and the derivative here. So when a function is decreasing, okay, remember the person is walking down. They're going left to right, they're going down. All right, what you're seeing here is the derivative, the slope of the tangent line, is negative. Okay, so negative derivative when a function is decreasing. Here, when a function is constant, okay, when the person's walking across it, it's a horizontal line, so the derivative, the slope of the tangent line, is 0. And then when they're increasing, the person's walking up the graph, we see that the slope of the tangent line of this graph is positive. Okay, so what we're hinting at here, what we're hinting at with this graph here, the sign of the first derivative can be used to determine increasing, decreasing. And you're going to see that in a couple minutes when I do the first two examples, how we're going to use the derivative here. So this is going to be this test for increasing and decreasing function. All right. So let's let f be a function that is continuous on the closed interval from a to b, and it's differentiable on the open interval a to b. Okay. If f prime of x is greater than 0 for all x in that open interval a to b, then what we can say is f is increasing on a to b. Now, if f prime of x is less than 0 for all x in a to b, then what we can say is f is decreasing on that closed interval a to b. And if f prime of x is equal to 0, okay, all right, for all x in a to b, then f is constant on that interval a to b. All right, so again, what we're looking at is the sign of the first derivative, okay? Sign is positive of the first derivative, increasing. Sign is negative, decreasing. Sign is equal to, the sign of the first derivative is equal to 0, constant, all right? So here's the steps. This is what we're going to do, okay? So these are going to be the guidelines for finding intervals on which a function is increasing or decreasing. And even before I list all these, okay, I just want to say this. The first part of this lecture is very wordy, and I'm throwing a lot of stuff at you. But I promise, after you see the first example or two, you're going to get the process down, and you're going to be, oh, okay, this makes sense. All right, so here's what we do. We're going to let f be continuous on some open interval from a to b. Okay, to find the open intervals on which f is increasing or decreasing, we use the following steps. All right, so we have this function. First thing we're going to do is we're going to locate the critical numbers of f in some interval a to b, okay? Critical numbers, just recall, so critical numbers occur when f prime of x is equal to 0. So, we've done that, okay? And then what we're going to do is we're going to use these numbers to determine test intervals. So what you're going to see me is I'm going to look at the domain of the function, and then I'm going to carve up the domain of the function into intervals, okay, that are separated by these critical numbers. That'll make sense when we get it in a second. Next, what we're going to do is we're going to determine the sign of f prime of x at one test value in each interval, okay? And then what we're going to do is you're going to use this theorem here, this theorem 4.5 right here, all right, to determine whether f is increasing or decreasing on the intervals. Okay, these guidelines are also valid when the interval is a to b, when that interval a to b is replaced with an interval of the following form. So like negative infinity to b, a to infinity, or negative infinity to infinity. And you will literally see in the first example here. Okay, so I'm going to start with a real simple one here. All right, and we'll start with one of the easiest ones. All right, so let's consider f of x is equal to x squared. All right, over here I'm going to sketch the graph of it. All right. And this is just what it basically looks like here. Just a very simple problem. A lot of times students say, and I go, okay, what is the interval this function is increasing or decreasing on? And a lot of times students will say, oh, it's increasing because it's always going up. But you got to remember, you're looking as you go left to right. So again, imagine, I know it seems silly, but imagine that person walking on the graph, okay? As the person goes left to right, he's going down. He or she is going down on this side of the graph. So it looks like the graph is going to be decreasing. This goes all the way to negative infinity, x does here. So looks like it's going to go decreasing from negative infinity to 0. And then after they get to 0, what's going to happen is the person's going to start walking upward. So it's going to be increasing from 0 to infinity. Okay, so it's like, I got that, okay, just by looking at the graph. That makes sense. As I go left to right, Over here, I'm going down, 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 so I'm decreasing, and then as I go left to right on this side, I'm increasing. All right, so let's apply the concepts and confirm this with this procedure that we have. First thing, step one, okay? You're going to locate the critical numbers, okay? So looking at this, we can see the domain, with just a polynomial function, is negative infinity to infinity. So to find critical numbers, you're going to find the derivative, f prime of x. Well, the derivative of this is just 2x. And you're going to set it equal to 0. So you're just going to solve this, right? It's very easy. You divide by 2. And you get a critical number as x is equal to 0. That's our critical number. Next step, after you have the critical number, what you're going to do is you look back and you're going to use these numbers, in this case it's just a number, to determine test intervals. So you'll notice in the text, or how I'm going to do this, when I want to find these increasing, decreasing, what I do is I set up a little table here. Okay, the first column of the table is called intervals. Well, look, you're going to start at the left side of the domain. You're going to go from negative infinity, and then you're going to go to the first critical number. All right, then you're going to say, okay, so since there's no other critical number, I'm going to pick right back up at 0, and I'm going to go all the way to this end of the right side of the domain, which is infinity. Then what you do is you say, okay, I'm going to pick a test value inside the domain I have above. So I'm going to pick, I can pick any number, okay, any number between negative infinity and 0. I'll pick negative 1, and over here I'll pick 1, all right, because 1 is between 0 and infinity. So always, you're going to notice as I do these problems, I'm always going to pick the easiest number. Now what you're interested in is I've got a test value. That's what I just did, test value. Determine the sign of f prime of x at one test value in each interval. So my next column will be sign of f prime of x. Well, just so we're clear here, what is f prime, right? So f prime of x is just 2x. So f prime of negative 1, well, you're not actually interested in the value, you're only interested in the sign. So 2 times negative 1, well, that's less than 0, okay? So it's negative, that's what that's implying there. And then f prime of 1, well, 2 times 1 is 2, that's greater than 0. So what is our conclusion here? Well, look, in this interval, our test value is negative. So what we're saying here is if you pick any value in this interval, okay, the sign of the first derivative will always be negative. So it's decreasing on this interval here. And then the sign of the first derivative on evaluated our test value in this interval is positive. So that means it's increasing. So look, just like what we said over here. Negative infinity to 0, it's decreasing. Boom, we got it. And from 0 to infinity, it's increasing. Boom, we have it. So this function is decreasing on negative infinity to 0, and the function is increasing on 0 to infinity. All right, so that was only our first example. So I'm gonna do 4 examples. So this is our first one, right? So I'm gonna do 3 much harder ones, and hopefully, as you see me do these problems more and more, it'll begin to make sense. You're gonna notice the procedure is always the same. All right, so let's grab another one here. Let's consider this function here. And this one's going to be a little bit of algebraic intensity. So f of x is equal to x times the square root of 9 minus x squared. Okay, so the first thing I'm going to do is I'm going to look at this. I'm going to say, okay, what is the domain of this function? Well, you can never have a negative under the square root sign, right? Then you get an imaginary number. So the domain is 9 minus x squared has to be greater than or equal to 0, and that'll hold for all numbers between -3 and 3. Okay. All right. So again, what you have to do is you have to find the critical values. All right. So you have to find the first derivative. Right, so to find the first derivative, what you're going to have to do is you're going to have to use the product rule. Right, so the derivative of this is 1 times this plus x. And then this, all right, I'm going to write it as 9 minus x squared to the 1/2 power. So then I bring the 1/2 down, get 9 minus x squared. 1/2 minus 1 is minus 1/2. And then the derivative of the inside is minus 2x. Okay, so unfortunately we have to clean this up. Okay, and you're going to notice that this is going to get really intense, really intense. Okay, so this is the square root of 9 minus x squared. I have a negative, so minus 1/2 and 2 cancel. Okay, x times x gets me x squared all over the square root of 9 minus x squared, because I'm just bringing that down. All right, just so we're clear, the 2's went away because the 1/2 and the 2 cancel out. So what I'm going to have to do is I'm going to put this over a common denominator to solve it, right? So the common denominator here, this is really over 1. So what I'm going to do is I'm going to multiply into this first one a 9 minus x squared, or square root of 9 minus x squared. Well, when I multiply the square root of 9 minus x squared times, in the numerator here, 9 minus x squared, you just get 9 minus x squared. So now you're able to combine it. You end up getting 9 minus 2x squared. All right, now to find the critical values, what you do here is you take this and you set it equal to 0 to find critical values. Or these critical numbers. I call them critical values sometimes. So I have 9 minus 2x squared all over the square root of 9 minus x squared is equal to 0. Well, since you want it to be equal to 0, you just want the numerator to be equal to 0 here. And there, there's no common value that'll make the numerator equal 0. Will also make the denominator equal 0. So you're really just solving 9 minus 2x squared is equal to 0. You're going to add this over. You get 2x squared is equal to 9. Divide by 2. And then when you take a square root to solve, x is equal to plus or minus the square root of 9/2, which are plus or minus 3 over the square root of 2. Or when you rationalize the denominator. Oh, geez. Okay, so we have two critical values. Okay, we have two critical values. We have negative 3 square roots of 2 comma 2, or divided by 2, and then the other one is 3 square root of 2 divided by 2. Okay, so if you notice in the previous problem, we only had one critical value. Here we have 2. All right, so again, what we're going to do is we're going to set up this table here, okay? So I'm going to go to the next slide for this. All right, so you're going to have your intervals. Okay, so just so we're clear here, right? Our domain was -3 to 3. And the critical numbers were going back -3 square root of 2 over 2 and +3 square root of 2 over 2. All right, so interval. You need your intervals, set those up. You're going to have to start here at the right end of the domain. So it's going to be negative 3, and then you're going to go, okay, what's the next critical value? Oh, okay, it's negative 3 square root of 2. And then you're going to pick up right at negative 3 square root of 2 over 2. And you don't go to 3. You go to the next value of all these, of either the domain ends or the critical numbers, which is 3 square root of 2 over 2. And then your last interval, you're going to pick right back up at 3 square root of 2 over 2. And you're going to go all the way to 3. All right, then the next thing you need is a test value. So it's like, well, what exactly is, negative 3 square root of 2 over 2, right? So like you can grab a calculator for this. All right, so let's just figure that out, right? So like 2 square root times 3 divided by 2. It's, it's like, let me just make sure I did that right. Don't feel I did. 2 square root, there we go, times 3 equal, divide by 2. There we go. So it's 2.12. Always check your work. It didn't seem right when I first did it. So, with the a number between negative 3 and negative 2.12, I'm going to pick negative 2.5. Here, I'm going to pick 0. That's easy. And over here, I'm going to pick 2.5. Next thing you want is you're going to want the sign of f prime of x here. All right, so let me go back, okay, just so you have it. This is our simplified derivative here, okay, so I'm just going to write it over here. F prime of x here is equal to 9 minus 2x squared all over the square root of 9 minus x squared. All right, so you're only interested in the sign. So whenever this is really important, and you're going to notice that I do this a lot, okay? If I'm interested in the sign here, the denominator will always be positive, so I'm really only interested in the sign of the numerator, right? So think about this. If you square negative 2.5 becomes positive times 2, that number is definitely greater than 9. You can plug that into your calculator here and verify that for yourself. All right, so that's negative. If you plug 0 in, you just get 9 minus 0, so f prime of 0 is positive. And then the same thing over here. So what you see here, okay, what our conclusions are? Well, in this interval, it's decreasing because the sign of the first derivative is negative. Over here, it's increasing because the sign of the first derivative is positive. And then same thing over here. It's decreasing because the sign of the first derivative is negative. So this function, you can just write it, you can even break it down more or write it all out fully here, is decreasing on negative 3 to negative 3 square root of 2 over 2, and also this interval here. And then it's only increasing on this interval here. All right, class, I know this was a lot to take in. So I'm going to follow this lecture up with a trig example, and then I'll do a transcendental function one as well, so you can see what that one, how you would tackle that.